Hello everyone. So last video we talked about area. Okay, we talked specifically about area under the curve. Under a curve. And at the very end of the video, I introduced a concept known as the definite integral. Now, we have found indefinite integrals in the past, okay? The definite integral, so we've done indefinite integrals, okay, about 2 or 3 videos ago. Now, the definite integral is written almost the same way, except you have these two numbers on the top and bottom of the integral sign. Okay? Now, the definite integral, this is a notation, okay, and it is equal to the limit as n approaches infinity of the sum at I equals 1 to n of f of x sub I, where x sub I is the x coordinate of each subinterval, times delta x. You could also write it as the limit as delta x approaches 0 of the sum of I equals 1 to n, because we told about last video how as you increase the number of rectangles, the width of the rectangles gets smaller. Okay, if you haven't watched last video, make sure you watch it, since some of these concepts will return. And this is the definition of the definite integral. Okay, you can geometrically or graphically, okay, define the definite integral from a to b of f of x dx as the area under the curve from a to b. Equals this area. So this is the top one is a formal definition. This is more of a visual definition of your definite integral. Okay? So knowing that we originally used rectangles, we can only approximate definite integrals as of right now. Okay? Because we don't have the tools that we need to evaluate some of them exactly. So we can resort to approximation techniques. Okay? And before we get into that, let's learn some properties of the definite integral. So if you're given a definite integral from a to b of f of x dx, then property 1, the definite integral from a to a of f of x dx is always equal to 0. Okay? From f of x dx, it will always be equal to 0. Because you're taking, if we draw a graph over here, this is A, this is B, from A to A, you're literally not catching any area. Okay? So by common sense, this integral should be 0. So let me just shade this in so we get our definition, area under the curve. Our second one is that if we have a point C such that A is less than C, which is less than B, so C is in our interval, then the integral from a to c of f of x dx plus the integral from c to b of f of x dx equals the integral from a to b. And again, from our little drawing, you can see how that's true. Okay? You can see that's true because you're literally adding the two areas together. If you were to see this is area 1 from A to C and area 2, then your overall area will be area 1 plus area 2. By common sense, you can derive the second property this way. Now, the third property, can't really derive visually, but you can prove it, is that the definite integral, okay, from b to a of f of x dx. So if you were to switch the limits of integration, you can do that, but you would have to take the negative of the integral. So 3 is also a powerful tool. In many AP questions, they will sometimes ask you to take an integral where the upper limit, so what the top number is called, is lower than the lower limit. So you would have to switch the limits of integration and take the negative so that you can actually evaluate this integral. So let's get into some approximation techniques. Note that all the properties of the indefinite integral are the same for the definite integral. In fact, let's do a problem right now. Okay, let's do a problem right now. Let's do a quick and easy one. So if we were to have a couple of functions, okay, a couple of functions, such that the integral from 2 to 4, right, from 2 to 6 of f of x dx equals 10, and the integral from 2 to 6 of g of x dx equals -2. Let's try to find the integral from 2 to 6 of 3f of x plus 2g of x dx. Now you can break this integral apart. Remember, the definite integral has the same properties as the indefinite integral. So you can split the integral apart. I can pull out the constant terms. And you're left with the information they already gave you. Okay, so we're given these two integrals in the forms of numbers. So you can just write this as 3 times 10 plus 2 times -2. That's 30 minus 4 is 26. Okay, now you can do stuff like this, okay? However, we cannot evaluate them just yet, okay? So we're going to have to resort to approximation, which is usually a question on the AP exam. Approximation techniques. Okay, so the first one is a left or right Riemann sum. And even though it sounds difficult, it's the rectangle thing we did, applied to a certain number of rectangles. Okay? So let's try to approximate the area under f of x equals x squared from 0 to 2 using a right Riemann sum with subintervals of 4. So we're having 4 rectangles. So let's divide this into 4. Okay? So the length of each subinterval would be 0.5. Now because it's a right sum, okay, the right edge touches your function. Okay, so you want to find the area of these 4 rectangles over here. These 4 rectangles. So the area of rectangle number 1 is 0.5 times 0.5 squared. The area of our second rectangle is 0.5 times 1 squared, or just 0.5. The area of our third rectangle is 0.5 times 1.5 squared. And the area of our fourth rectangle is 0.5 times 2 squared. Okay? So let's plug this into a calculator. Usually these problems are calculator questions. Okay, so I got my calculator. So I have 0.5 times 0.5 squared plus 0.5 times 1 squared plus 0.5 times 1.5 squared plus 0.5 times 2 squared, 4. Okay, so what does that evaluate to? We get 3.75. Yep, we got 3.75. The actual area, is, I think I remember this from last video, we did this, is 8 over 3. Yes, we have 8 over 3, which is equal to 2.666 and so on. So this is actually an overestimate, okay? But it's not terrible, okay? At least it's not more than 2 apart. It's not more than 2 from the actual value. So it's not terrible, it can be better, okay? It is an overestimate because your function is increasing. Okay, so you have more of this outside edge rather than parts of it not being filled. Okay, so this is an overestimate. If we can evaluate the left Riemann sum, well, our first one will be 0.5 times 0 squared, which is 0, plus, let's draw this rectangle, 0.5 times 0.5 squared. Draw this rectangle, we have 0.5 times 1 squared. Draw this rectangle, and we have 0.5 times 1.5 squared. Okay? So the reason why we're squaring it is that, f of x is x squared. Okay, so it's f of x times delta x. So if we evaluate this right now, we get over here. Okay, so you get 1.75. which means it's an underestimate. Okay, and it makes sense since you have a little area left over here, a little more. So you can see that the actual area is between the left and right Riemann sums. The actual area is between our left and right Riemann sums. So there's another approximation technique that you can use, a little more accurate. It's called a midpoint sum, or midpoint Riemann sum. So the midpoint sum, we're going to draw x squared again, is drawing the rectangles to be a little more accurate. So we're going to see how to draw these types of rectangles. So we're taking it from 0 to 2, 0 to 2, and now we're going to try to approximate the area using a midpoint sum with 4 rectangles. So again, we have subintervals of 0.5, that's the length. Now, instead of doing either the left or the right, the rectangle will intersect the graph at the midpoint of the intervals, why it's called midpoint sum. So this will be 0.25. This rectangle will intersect at 0.75, your midpoint. Okay, and now you can see why this will be a little more accurate. It's because some of it will be in, some of it will be out. Some of it will be in, some of it will be out. Okay, so you have 4 rectangles right now. So each of them has a length of 0.5. Okay, so 0.5 times f of the midpoint, so f of 0.25. That's 0.25 squared plus 0.5 times this midpoint, f of 0.75 squared, plus 0.5 times, what's this midpoint? Well, this is 1, this is 1.25. Remember, the rectangle hits the graph instead of the left or the right. It hits it such that it hits the function at the very center of the rectangle. That's why it's called a midpoint sum. So this is 1.25. And our final one will be 0.5 times 1.75 squared. And if we evaluate this sum, let's put in a calculator, 0.75 squared plus 0.5 times 1.25 squared plus 0.5 times 1.75 squared, we get 2.625. And the actual area is 8 over 3 equals 2.666. So now you can see it's a lot closer. It's a lot more accurate. And the reason being is that you have a fair balance of outside area and inside area that is neglected. So the errors will sort of cancel out in the process. Not completely, but enough so that it creates a much more accurate representation. However, the most accurate, okay, will be this third method of approximation that you need to know, which is known as the trapezoidal sum. And now I can see where we're going to go to. A trapezoid. We're going to use trapezoids to approximate our sum. So I'm going to draw a bigger graph. This will be 2. So let's make this 2 is 4. Okay? So we want to find this area as we did before, but instead we're going to use trapezoids. 4 trapezoids, no rectangles, but trapezoids now. So if I were to make 4 trapezoids, the subinterval part stays the same for each approximation technique. So I have 4 subintervals here. However, now use trapezoids. Okay? So you have this trapezoid, this trapezoid, and this trapezoid. And you have this trapezoid, which turns out to be kind of a triangle. Okay, since this is 0. So how do we do this? So we would basically find the area of all the trapezoids. So that is 1/2 times the area of a trapezoid is 1/2 times the height times base 1 plus base 2. So because the height will be the same, this is your height, you can 1/2 times the height times base 1 plus base 2, then base 1 plus base 2, base 1 plus base 2, base 1 plus base 2. Okay? Whoops. It's not the values, it's the f of them. Okay, so it is base 1, which is 0, plus base 2, 0.5 squared. Remember, it's the function values. This is f, okay? I accidentally put the x coordinate. Plus base 2, f of 0.5 plus f of 1 plus 1 squared plus 1.5 squared plus 1.5 squared plus 2 squared. Okay, and all we need to do is add this up. And let's see what approximation we get now. So 0 plus 5 squared plus 2 times 1. And we get 2.75, which is, again, not bad. It's only 0.09, about 0.09 units off, okay? So this is also an accurate way. Okay, so you can kind of rank them in accuracy. So you have left and right Riemann sums. This is the least accurate, usually. And then you have the midpoint sum. Well, you can sort of, it's kind of a tie. You have the midpoint sum. The midpoint sum is actually more accurate for this, was more accurate in the approximation. The midpoint sum and the trapezoid rule for most accurate. For the most accurate. There are more ways you can approximate them, but the AP exam usually requires only the the left and right Riemann sums, the midpoint sum, and trapezoid rule. Okay, so far you might have noticed we have only approximated functions. Okay, we've only approximated definite integrals. However, next video, we will actually figure out how to calculate them. Okay? And just as a final problem, this will be important to us next video, we're going to try to express this as an integral, because you're going to need to find out how to express certain areas as integral expressions. Okay, so let's say you're given this function. You want to find the area of this region. So how would you write an integral expression? Okay, this is f of x equals sine of x. Or this is 0 and this is pi. So the area, you're going from 0 to pi. So that will be your upper limit is pi, so your upper number, your lower limit is 0, and you're trying to find the area of the region bounded by sine of x and your variable of integration. And next video, we're going to learn how to actually evaluate this integral so we can get the exact area of this region and a lot more regions. Let's do one more. Let's say we had the function g of x equals the cube root of x. Okay? And it meets this at 8. And we want to find, it's the line y equals 2, we want to find the area of this region. So what would you do? Well, you could do it in two ways. The first way would be to take 2 to 8. So you would do 16, it's your area of the rectangle, minus the integral from 8 to 0 of the cube root of x dx. Right? Because it's the entire rectangle area minus this blue area. However, there's a slightly better way to do it, and it's to convert this function as a function of y. And if you were to turn this into a function of y, g of y equals y cubed, then you have a much easier integral. If you were to rotate this on its side, then you would simply have to evaluate the integral from 2 to 0. Remember, you have to switch the limits because we're in y coordinates now, of y cubed dy. You have to make sure the variables and the limits of integration match. And this is also a way to find out this area. And all in the next video, we're going to learn how to calculate these areas and these definite integrals using probably one of the most important theorems in calculus. Thanks for watching. If you have any questions, please comment, like this video, and I hope to see you soon in the next video.